In the previous section, we demonstrated what can happen when certain hazardous materials chemically react. These are the physical and chemical properties that you're most concerned with because they directly affect your health and safety. But as yet, we haven't discussed why hazardous materials react the way they do. For example, why will cooling a container of gas in a fire help prevent a levy? Why is ammonium nitrate mixed with fuel oil an effective blasting agent? What accounts for the different flash points of hydrocarbons such as propane and gasoline? In this module, covering basic chemistry, we'll answer these questions and many others to take a closer look at the cause behind the effect. You may wonder if a knowledge of chemistry is necessary. Do you really need to understand atomic structure, molecular bonding, or the organization of the periodic table? Absolutely. A knowledge of chemistry will not only help you remember some of the more unique properties of chemicals, it will also help you predict reactions. Many chemicals are members of the same group of elements and react in similar ways. Understanding these relationships can help guide your initial actions in an emergency even when you're not familiar with the chemicals involved. All matter is made up of combinations of individual chemical units called atoms. Substances made up of only one kind of atom are called elements. There are just over 100 elements, each with its own chemical symbol and individual characteristics. Without a structure for organizing these elements, there would be no way to identify relationships among groups of elements. This is the purpose of the periodic table. In the periodic table, for example, elements are organized by atomic number, beginning with atomic number 1, hydrogen, and increasing one number at a time. The atomic number represents the number of protons in the nucleus of each atom of that element. It's also the number of electrons surrounding the nucleus. The atoms for each element grow larger and heavier as their atomic numbers increase. Elements are also generally arranged according to their physical state at room temperature. Here, solids are shown as green, liquids as yellow, and gases as red. The periodic table separates metals from nonmetals. Metals are known for their ability to conduct electricity. Metals are shown as blue here. Nonmetals are gray. Most of the radioactive elements, with a few exceptions, are located at the bottom of the table. Perhaps most important to hazmat team members, though, are the similarities that unite elements. Elements that are near one another on the periodic table tend to be similar in their appearance and chemical behavior, particularly those elements in vertical columns. For example, there are 6 naturally occurring gases that are called noble gases because none of them easily react with other elements. These gases are arranged in one column to the far right of the table. Because they're so stable, these gases don't support combustion. In addition to the noble gases, there are other groups of elements that share similar properties. For example, the second column from the right contains fluorine, chlorine, and 3 other elements. This group, known as the halogens, are all strong oxidizing agents. The reactivity of elements in this group decreases as atomic number increases. Fluorine, with an atomic number of 9, is the most powerful and dangerous oxidizing agent of the group. Iodine, with an atomic number of 53, is one of the least reactive. Halogens are also corrosive in high concentrations because of their tendency to react with moisture to form acids. When mixed with water, for example, chlorine forms hydrochloric acid, which can cause permanent damage to body tissue and metals. Lithium, sodium, potassium, and the 3 other elements in the far left column are all alkali metals and possess similar properties. They're soft, light, have low melting points, and high heat conductivity. More importantly, they're water reactive. A demonstration from the previous module illustrated the water reactivity of sodium. Another demonstration shows the same characteristics for lithium and potassium. The lithium used in this experiment fizzes and bubbles when dropped into water. However, the reaction is somewhat less dramatic than that of a similar-sized piece of sodium because of sodium's greater atomic number. Potassium shares this water-reactive property with lithium and sodium, but because it has a greater atomic number than sodium, it reacts with water much more violently. Potassium also has a lower melting point, which allows it to spread over the water more quickly and causes a faster reaction. The group of elements second from the left on the periodic table, known as the alkaline earth metals, are flammable and their dusts are explosive in air. This group includes beryllium, magnesium, calcium, and other elements. Unlike chemical behavior, toxic effects are not predictable from the periodic table. Beryllium, for example, is highly toxic and carcinogenic, while calcium is not. What accounts for the similar properties within a group of elements? The answer lies in the number of electrons in the outer layer or shell of an atom. Electrons are negatively charged particles that orbit the positively charged nucleus of the atom within a shell. The largest atom has a maximum of 7 shells. Each shell can hold a limited number of electrons, but it's the number of electrons in the outer shell that is most important, because this determines how one element will react with another. All atoms seek to have only full outermost shells. This is accomplished by gaining or losing electrons. The groups of elements on the far left of the periodic table tend to be reactive because their atoms have only 1 or 2 electrons in their outer shells. The groups on the far right, with the exception of the noble gases, need 1 or 2 electrons to complete a full shell, so they also tend to be reactive. The noble gases have full outer shells, so they won't easily react with other elements to gain or lose electrons. Molecules are formed when 2 or more atoms bond together as a result of interaction among the electrons in their outer shells. This process is what we call a chemical reaction. Remember that substances made up of one kind of atom are elements. Substances made from the bonding of 2 or more different atoms are called compounds. Energy is either released or absorbed during the bonding process. We can demonstrate how a compound is formed in an experiment using sodium metal and chlorine gas. The sodium has a tendency to lose an electron, the chlorine to gain an electron. When this piece of sodium metal is heated and placed into a container of chlorine gas, you can see the energy that's released in the form of intense heat and light. This is the result of a chemical reaction taking place. The crystalline material that's formed from this reaction is sodium chloride, common table salt. It's a compound with a new molecular structure and totally different chemical and physical characteristics. Whether electrons are gained, lost, or shared, chemical reactions often produce energy. Ammonium nitrate mixed with fuel oil, ANFO, is commonly used as a blasting agent in construction. Ammonium nitrate molecule is unstable. When heated, its weak bonds break apart and the nitrogen atoms recombine to form nitrogen gas molecules. Some of the oxygen from the reaction combines with the hydrogen atoms to form water. The rest is used to burn the fuel oil. Earlier we discussed how the periodic table helps illustrate the reactivity of atoms of various elements. However, other factors influence the rate and nature of chemical reactions as well. Very fast reactions produce explosions. The speed of the reaction we just saw, for example, was increased by placing detonators with the ANFO mixture. On detonation, this explosive supplied the intense heat needed to increase the rate of the reaction. In addition to temperature, the rate and nature of a chemical reaction can be affected by the concentration and total amount of materials involved, an increase or decrease in pressure, and the presence of catalysts. In chemicals that are gases, the effects of temperature and pressure are interrelated, as shown in this experiment. For simplification, we're producing a physical change, not a chemical reaction. When this metal ball filled with the gas is heated, notice that the pressure of the gas inside the ball increases. When the heat is removed, the pressure remains high, although it will gradually fall as the ball cools. To speed up the drop in pressure, the ball is immersed in an ice water bath. Notice that the pressure begins to fall very quickly. We can better understand the relationship between temperature and pressure if we examine what's happening inside the ball. Gas molecules move freely inside the ball. When they strike the walls, they exert a certain amount of force, reflected on the reading of the pressure gauge. When temperature increases, the molecules move more quickly, striking the walls with greater force. An increase in force means a corresponding increase in pressure. Stated another way, gas expands when heated and contracts when cooled. When the ball is cooled with ice water, the speed of the molecules slows down, and the pressure inside the ball also drops. The concentration and total amount of the materials will also determine the nature and rate of the reaction. When a piece of wood is ignited with a match, it burns because the oxygen in the air reacts with the wood. The percentage of oxygen in air is about 21%, causing the wood to burn at a moderate rate. However, when the burning wood is placed in an atmosphere containing 100% oxygen, it burns much more intensely. The higher concentration of the oxygen speeds up the rate of reaction. This is the reason that oxygen-enriched environments are so hazardous. Catalysts are often used to change the rate of chemical reactions. A catalyst can be defined as any material that speeds up a chemical reaction but is unchanged at the end of the reaction. In this demonstration, sodium potassium tartrate is dissolved in warm water. To break down this compound's large molecules, we add hydrogen peroxide. But notice that there's no visible evidence because the chemical reaction is taking place so slowly. To speed up the reaction, we add cobalt chloride, a catalyst. The solution gives off steam, foams, and eventually turns green, indicating that a chemical reaction is taking place. Remember that a catalyst has two important properties. One property is that it affects the rate of reaction. Here, the cobalt chloride has increased the rate of reaction. The second property is that a catalyst is unchanged at the end of the reaction. Notice that when the reaction is over, the cobalt chloride returns to its original pink color, indicating that it is the same as before the reaction. Most of the demonstrations we've seen so far have involved a major class of chemicals, inorganic chemicals. The other major class is organic chemicals. Inorganic molecules are usually smaller and simpler than organic molecules. Organic compounds always contain carbon. They tend to be more complex because carbon atoms have the ability to link with each other through covalent bonding to form large, complex molecules. Those that are composed primarily of hydrogen and carbon are called hydrocarbons. Many hydrocarbons are derived from crude oil. Hydrocarbons pose special dangers to firefighters because most of the members of this group of compounds are flammable or combustible. There are various types of hydrocarbons, each with slightly different chemical properties and widely divergent industrial uses. To better understand these different properties, we should begin with a look at the process that separates the various types of hydrocarbons from crude oil. The process is commonly called fractionation or distillation. During this process, crude oil is heated and fed into a tower-like vessel where the components are separated according to their boiling points. Heavier hydrocarbon molecules remain near the bottom of the tower as thick liquid. Lighter molecules rise toward the top of the tower. Here, these light or low boiling point molecules are drawn off as gases such as ethane, propane, and butane. At lower levels, heavier hydrocarbons are drawn off as gasoline, kerosene, diesel oil, and so on. This process leads to another question. Why are some hydrocarbon molecules lighter than others? The weight of the molecule is influenced by the number of carbon atoms that make up the molecule. A single carbon atom can bond with 4 hydrogen atoms, as in a methane molecule. 2 carbon atoms can bond with 6 hydrogen atoms, as in ethane, and so on. The ability of a carbon atom to form up to 4 covalent bonds with other carbon atoms means that long chains can be formed. The number of carbon atoms generally determines the properties of the hydrocarbon molecule. In general, the boiling point, melting point, and flash point increase with an increase in the number of carbon atoms in a chain. The length of the chain also determines the state of the hydrocarbon at room temperature. Shorter chains are normally in a gaseous state. Longer ones are liquid. Hydrocarbons that bond in straight or branched chains are called aliphatic hydrocarbons. Those that bond in simple or complex rings are called aromatic hydrocarbons. If any atom in a hydrocarbon chain or ring is replaced with another atom or group of atoms, the new molecule is often called a hydrocarbon derivative. These molecules are often flammable or combustible since they're derived from hydrocarbons, but they may have other, more dangerous characteristics. The specific properties of a hydrocarbon derivative are determined by the atom or group of atoms that is added. This atom or group of atoms is often referred to as the functional group. For example, when a halogen such as chlorine becomes the functional group of a hydrocarbon chain, the derivative is known as a halogenated hydrocarbon, such as the methyl chloride shown here. These derivatives possess different properties from their parent hydrocarbons. In this case, methyl chloride is more toxic and has a much higher boiling point than its parent, methane. When the functional group is composed of a hydroxyl, a hydrogen and oxygen combination, the resulting hydrocarbon derivative is an alcohol, such as ethyl alcohol. Alcohols burn readily and produce very hot fires. They're considered moderately toxic. One exception is methyl alcohol, which is very toxic and often causes blindness. Some hydrocarbons that contain oxygen can react with oxygen molecules from the air to form peroxides. Diethyl ether, for example, forms unstable peroxides when exposed to air for a period of time. The remaining diethyl ether evaporates, leaving only the peroxide. All peroxides are very unstable due to the weak bond between the oxygen atoms. As a result, they're a serious fire and explosion hazard. This is why old bottles of ether are extremely dangerous to handle. Hydrocarbon derivatives that contain a carbon atom linked to an oxygen atom by means of a double bond are called carbonyls. Carbonyls include ketones, such as the acetone shown in this formula, and aldehydes, such as acetaldehydes. When a carbonyl group also has a hydroxyl group on the same carbon, it's called a carboxyl. One example of a hydrocarbon with this group is acetic acid. All these substances burn, and each has its own specific dangers. Small hydrocarbon molecules can be linked together at the site of their functional group to form polymers. In this example, ethylene serves as the building block, a monomer. The functional group in ethylene is the double bond. When a catalyst such as this organic peroxide is added, it forces the double bond to open. The open bond joins with another ethylene and forces its double bond to open. This open bond, in turn, joins with another ethylene, and so on, until chains of as many as 800 molecules are formed. The reaction stops when two chains link up. There are thousands of hydrocarbon derivatives, each with its own hazardous properties. You obviously can't memorize all of them, but you can remember two basic points. Since they're derived from hydrocarbons, most of these compounds are flammable and combustible. However, other properties, which may be more or less dangerous, are determined by the functional group. Understanding chemical properties is essential in recognizing a hazard. However, operational decisions must be based on the specific identity of the chemicals involved and on reference information, not on generalizations. Basic chemistry provides you with a foundation. By adding other knowledge, skills, and resources to this foundation, you can build a system for making decisions that will result in a safe and effective response.